All right, this is review day 3. We're looking at chapter 10 through 20. I know that sounds like a lot, but we skipped a bunch of chapters. So it's basically simple harmonic motion, waves, sound, and electricity, and what you need to know for those chapters. So here we go. First thing you need to understand is Hooke's law, which is F equals negative kx. Remember, the negative just means it's a restoring force. The smaller the spring, the bigger the k. If it's the same material, it's an inverse relationship. So you keep cutting it in half, right? Then you double the k if you cut it in thirds. So I shouldn't really say smaller spring, but if you cut the same spring, right? It's got to be the same material. Everything's got to be the same. So if I take my spring and then I cut it in half, then this k is going to be 2k of what the k was for the whole thing because it got smaller. The spring, if you're doing Hooke's law, the spring cannot be moving. It's just displaced to be able to use that equation F equals kx. Because if it's moving up and down, the F is changing constantly. So then it just doesn't work, right? So you're always looking for the displacement from the original, right? When you're looking at it, I think we thought. Simple harmonic motion, they do give you a couple of these equations. I know for sure they give you x equals a cosine omega t. No, they give you W equals 2 pi F. Not 100% sure. I think they give you this one, but you might want to double check. But it's just the derivative, right? So we just pull it out, turns to a sine. So it's A omega. But if you think about it, that's just R omega, which was equal to V, right? So it's the same thing. And this is R omega squared, which was equal to AC. So it's all the same thing we've seen before. It's not like it's new. And so when we're doing simple harmonic motion, you're always free to use those equations. You do need to use that one a lot. Omega equals 2 pi F. And then remember, T is equal to 1 over F. I think they actually do it. I always do it upside down when I do it. So I always use both of these separately so I don't mess it up and put it up down. If you're in simple harmonic motion, it must be moving. In the middle, you have the maximum kinetic energy, so you can think of it as a pendulum, right? Sometimes that helps. And so right here in the center, we have the max KE, and at the endpoints, we have the max UG, right? The max UG, and then they have everything in between, right? So it's opposite, it's minimum, right? It's when we're at the bottom, we have the minimum UG, and at the top we have the minimum KE, right? Minimum KE. But that makes sense. And it could be a spring, right? That's bouncing back and forth. Same concept. In the center, we still have the maximum KE and the minimum UG. The energy of a spring, remember, is 1/2 kx squared. It comes from our graph because when you graph it with Hooke's law of F versus X, and we want to find the work, and work is equal to the area. I didn't say that in the other review, so remember that the work is equal to the area under an Fx graph, right? If I take the area under here, then it's always going to be a triangle, which is why it's 1/2. And we know that F is equal to kx, so that would make sense, therefore, that it's 1/2 kx times x, which of course is 1/2 kx squared. But it looks kind of like 1/2 mv squared, so it's easy to remember as well. And if we're looking at frequencies of a spring, they give you, I think, the period one. So I think on the equation sheet it says T of a spring is equal to 2 pi square root of m over k, and TP is equal to 2 pi square root of L over G. But it doesn't matter which way you look at it. It's the same thing. Remember, you can convert this. This is just regular frequency. You can also convert it to omega, which would just be in radians. That'd be that's angular, right? Angular frequency. So some of you got messed up because when you read the question, you don't catch what it says. So you got to figure out what they want, or at least put the right units so they know you know what you're talking about, because periods in seconds and frequencies in hertz and omegas and radians per second, but it's all the same thing as far as simple harmonic motion goes. Then we got into wave speed. And we looked at waves, and we know that the wave depends on the medium. It can depend on the tension. It can depend on the temperature. It can depend on the mass, right? All of that is what it depends upon when we're dealing with speed. V always equals lambda f, and this is the square root of f. Remember, m over L is linear density. So I know it's weird because it seems like they put the L on the top, but it's the square root of F over M over L, and that F is tension, right? Because it's how hard you're pulling it. The more you pull on it, the faster it goes. The more linear density it has, the slower it goes. You should understand it's a sine wave. You should know where amplitude is, which is from the center to the top. You should know wavelength is measured from crest to crest or two identical points. If this has time on it, you should be able to find the period by finding two identical points, and then that would represent the period of the wave. So things like that. Those are pretty simple. I think most of you are cool with that. And then we talk more in depth about sound. And remember, sound is a longitudinal wave, which means it needs a medium. It's a mechanical wave. It's vibrations. If we're looking at sound intensity, right, that's intensity, then it's P over A. But if we're dealing with a point source and it's going out like this, then it's going to be the surface area of a sphere, which is 4 pi r squared, which means it follows the inverse square law. So if we double it, it's 1/4. If we triple the distance, it's 1/9, right? Back to inverse square law. They like to do comparisons, so I like to point out some of those comparisons when I don't know what they're going to ask you to compare. Then you have this thing called Doppler, which just means that if something's moving, it makes the frequency sound like it's different. Remember, this is apparent. It's not a true shift, because if the object stops, the frequency goes back to whatever it was. But if it's coming towards you like this, they get squished together. Notice the waves are really close together, so you have a higher frequency and a lower wavelength. And if it's going away, then it's at a lower frequency, higher wavelength, because they get pulled apart. And the faster, so the more you increase the V, then the more you hear the Doppler, right? So you get an even bigger shift, right? There is an equation. They're not going to ask you about the equation, or if they do, they'll give it to you. But you should understand that the faster you go, closer to the speed of the wave, the more Doppler you're going to get. Then we had talked a little bit about interference, and we talked about the fact that if something's in phase, you have constructive interference, and so that's when you have a crest lining up with a crest. We talked about the runners, and if you have everybody out of phase, if you start here, and then the other one, starts going the other way, so now you're out of phase, right? So this would be out of phase, and this one is in phase. So this one makes the amplitude go up, and this one makes the amplitude go down. And if it's in phase and travel the same distance, because you can keep doing that, right? If you shift a whole wavelength, then you can be back in phase. So we talked about this concept of a path length difference, right? The change in path length. If it's equal to a whole integer, I think we did m's like in Michael, but n, it doesn't matter. It's an integer. So if I keep changing it by 1 lambda or 2 lambdas or 3 lambdas, they're always going to be in phase. But if I change it by a half a lambda, 3 halves lambda, 5 half lambdas, then they're always out of phase. So when we talk about speakers, so you'd look at, here's the distance for one, and here's the distance for the other one, then my delta L is simply equal to L2 minus L1, and the concept is how much of a lambda is that equal to, and that will tell you if it's a maximum or if it's a minimum, and how many you could find between two separate points. And then we talked about beats, and beats are interference as well, and you just subtract, and if they're close enough, you can actually hear a beat frequency. It sounds like a wobble goes, right? And that would be beat frequency. Then we talked a little bit about diffraction, which is the spreading out of waves and making it go in all different directions. It's due to a barrier, so you have to have a hole someplace, or it could go around something, so you could have a wave going like this, and then it kind of bends around the corner. That's also considered diffraction, as well as going through a hole. It has to be close to the same size, because the equation is sine theta equals lambda over d, and since sine can't be more than 1, if d gets too small, then it's more than 1, right? And then that's impossible, so it basically bounces back. If it's a circular open, you put the 1.22 in front of it. I don't think they're going to ask you those kind of questions, or if they would, give you the equation, like I said, for any of these particular things. But they are going to want you to know that the bigger the lambda, the more the theta, so that means the more the diffraction. And if you have a bigger d, then you have a less of a theta, and you have less diffraction. But if it gets too small or too big, then it doesn't do any diffraction, right? Because it's too much. It either goes straight through or it bounces back. Then we talked about standing waves and harmonics, which is due to the waves bouncing back and forth and reflecting and interfering with each other. You should understand the concept of a node. So when they draw waves like this, right? So is this a standing wave on some sort of rope or something? We know these points right here are known as nodes. We know these points up here are antinodes, right? We know the first harmonic is going to be the biggest wave you can get. If it's an open-closed system, it's going to look like that. So this is a half a lambda, and this is a quarter of a lambda, and then you keep adding half a lambdas to it to get to the next one. So the wavelength gets smaller as you go up to the next harmonic, and the frequency gets higher, and so they're just integer values. So if I know F1 equals 3 hertz, then I know F2 is equal to 6 hertz. Now you have to be careful when you're doing the open-closed system because you only want 1, 3, 5, and 7. So F1 might be equal to 3 hertz, but you can't get an F2 on there, so you just jump right up to F3, and then that would be equal to 3 times, or that would be the second one, right? Not 3 times that. Oh my goodness. Well, yeah, 3 times that. So it'd be 9 hertz, right? Because we missed the 6. Yes, we can do math. So that's where we get the harmonics, right? Where it's N over 2L or NV over 4L. It's the same concept. It's just a way to do the math of it. It's basically V over lambda, right? Where lambda is equal to 2L, or it's equal to L, or whatever it happens to be. As you keep going up, you keep adding a half, so it'd be 3 halves L. In this one, it's equal to 1/4 L, and then it's equal to 3/4 L, and then 5/4 L. Right, so that's where the 4 comes in. That's why it's 1, 3, 5. Remember, get the concept, don't just memorize. Also should remember that the distance between any two antinodes, no matter what kind of wave you're talking about, is always lambda over 2, because if it's between antinodes, antinode to antinode, no matter what kind of wave you're talking about, is always a half of wavelength. Then we got into chapter 18 through 20, which was electric circuits, and we said, okay, Coulomb's law, F is equal to KQQ over R squared, and lo and behold, another inverse square law. Yes, they're just all over the place. Looks just like green M&Ms R squared. The negative and positive only tell you whether the charges attract or repel, so don't plug them in and get a negative force, because negative force is just telling you they attract, and positive is just telling you they repel. You need to figure out it's a vector, so, if I have a force here, if I have, charges here, and this is a positive, and this is a negative, and this is a positive, let's make them different colors. So make this one positive, and I want to figure out F here, the total force on the sum of the forces right there. Then I know the red one's going to pull it this way, and I know the blue one's going to pull it this way. So I would do the positives of them, and then I would just figure out that this is equal to F and then minus F, and whichever one's bigger tells me which one it is, and I do KQQ over R squared for both of those. So make sure you add resistors. Then we got into circuits. We know I is current, which is like the flow, like a river flows, and that's Q over T, and it's measured in amps, which is coulombs per second. If it is ohmic, if it is ohmic, then it obeys Ohm's law, which is V equals IR. They're going to tell you it's an ohmic resistor. Then you know V equals IR, so you know you can graph it and do V versus I and get a straight line, and the slope is equal to R. Remember, we talked about this. Everything can be graphed. Everything can be graphed. You're always trying to make graphs linear, so remember that. R is therefore equal to V over I, because that's the slope. R is also equal to rho L over A, where rho is resistivity. The idea is the longer a wire is, the more resistance there is, the bigger area, the easier it is to flow, so that makes the resistance go down. And resistivity is what it's made out of, and so some materials like gold are really good, have low resistivities, because they're super expensive, so we don't tend to use those. Copper is probably the best one to use, that's the cheapest, but you can go to aluminum, which is really bad. It has much more resistance, but it's a heck of a lot cheaper. And then we looked at power, which is work per time. We don't understand VQ over T, so just ignore that. Just trust me, it's IV, which is the same as I squared over R, which is the same as V squared over R. Well, that equation is true, the one I crossed off, we didn't talk about it, so don't worry about it. We don't know what VQ is. And then we talked about series versus parallel circuits, and we know for series circuits that the I total is equal to I1 is equal to I2 is equal to I3, because when I'm going in a series, right, everything is the same. There is one path for the current, and that's what it is. The voltage drops, though. You have a little bit drop here and a little bit drop here, and then it pumps it back up here. So this is positive V, negative, oops, I already had a V there. This is negative V, and this is negative V. So these two V's have to add up to that V, because this is giving me energy, and these are taking it away. That's the main concept you should understand. For resistance, we know that the resistance adds up because we know that this is IR, this is IR, this is IR. So if the I's are all the same, you cancel them out, and you end up with this. So we know in series that the resistance goes up, right? Because there's more things to go through, so it's harder to get through. And then finally, we talked about parallel circuits. You should understand a parallel circuit. Here's my parallel circuit. And so now the current is going to go in both directions. So that means I have 2I. So some of the current goes this way, and some, well, that actually would be my I total, right? And then some of the current goes this way, and some of the current goes that way. And if I add up these two, it should equal to this. That is conservation of charge, as opposed to the other one that was conservation of energy. Because they're hooked both to the battery, the voltage drop across here is the same as the voltage drop across there. And so therefore, when we add up the I's, right, it's going to be V over R. So since it's V over R plus V over R plus V over R, the V's go away, so we end up with the 1 over. So make sure you do that the right way. But that means that my R goes down. It's like I always say, you have a big gym, you open up all the doors, there's more space for the things to go out, and so therefore it goes faster. Okay, so this one, the challenge for you on this one is going to be to determine the frequency. You have to figure out the frequency of a motor. So there's a handheld motor, and you put it, oops, let's do this a little better. So there's going to be a motor down at the bottom, and it's attached to a string. You hold it with your hand. There's a lovely hand, and it's going to wiggle, 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 and you can use a strobe light if you'd like. And you need to figure out, based on the standing wave that you get, you need to figure out what the frequency of that motor is. I'm not going to tell you how to do it, but that's what you have to figure out. Again, you have to get the motor frequency. We check it. I'm trying to remember how but we will check it. We will check it, and it has to be within 10% in order to get the extra credit. All right, good luck.